Hi everybody, welcome back to Multirate Signal Processing, this time about transforms as filter banks. So let's start with equivalent analysis filters for a DFT. So last time we saw that the DFT as block processing is convenient for fast implementation and also perfect reconstruction. And here we will see that we can also interpret it as a filter bank indeed. So from our early definitions in lecture 2, we know that a DFT of a block of a signal x is defined as this equation here. So x of subband index k is the sum over the block of the signal multiplied by this transform kernel, the exponential function e to the minus j 2 pi over capital N times k times n. Right, so this is basically the same as a matrix multiplication of a vector x, a row vector x, times this matrix, which is generated by this exponential function over k and n. So we can rewrite the DFT as a matrix multiplication with the matrix T, which has these elements. So T at the nth row and the kth column has this entry here, this exponential function from this transform kernel. So n is the time and row index, and k is the frequency and column index. Both are in the range between 0 and capital N minus 1. So here we just use the signal block vector, which consists of n consecutive samples of our signal x. And then we can rewrite the DFT of this block as simply the multiplication x of block M times transform matrix T. And the result will be a set of subband values coming from the DFT for block number n. So Y contains n DFT coefficients. So this is the matrix formulation for the DFT. And the matrix multiplication in equation 3 that we just saw is simply this. And we can see that it's the same as the definition of the DFT. And we compare it here. So it's identical. Except here we have the block index lowercase m. Right? So we do this for each block of our signal x. So here we can now extract the equivalent impulse responses when we look at this equation. Now we can compare above our transform equation, the number 4, with the convolution and downsampling equation, equation number 2 of last time. So we saw this is what we got out of the filter bank equation, filtering including downsampling. So we have this downsampling by a factor of capital N for block lowercase m, and this was the equation for coming from the convolution, the downsampled convolution. So again, we also saw it in the definitions of lecture 1. So we see that here the index lowercase n for our signal x has a reverse order or reverse sign as in the transform equation 4. So here we have minus n, right? And here we had a plus n. So except for this, it's pretty much identical when you look at it. So here we have the sum going over n equals 0 to capital N minus 1. It's the same. Then we have an x. Here we have a block index mn. Then we have some freely choosable phase index n0. So we can also choose to set it to 0 if you want. But we have this minus sign here. So this minus sign does not fit to this plus sign here. So that means we have a time reversal relative to this coefficients from the filter impulse response. So basically this shows us that this kernel here corresponds to the time reversed impulse response. And this is actually what we'll see in a few few lines later. So we see here that the index has this reverse order, but since we are interested in the equivalent impulse response, we simply reverse the index order in the transform equation 4, right, with index substitution. N is replaced by n minus 1 minus n prime. So then basically we can fix this index reversal. So now we have this going over n prime, and now we have, instead of having plus lowercase n, we have plus n minus 1 minus n prime. Right. So basically now we try to make our transform equation number 4 more similar to the convolution equation from the filter bank. So now we turn this into a negative new index n prime, which we can see here. So now this fits to the convolution equation, and now we can also see here that we have the time reversal now in this transform kernel. So actually this shows now that our impulse response is the time reversed transform kernel from the DFT. So this yk of m, here's a modified notation that has the subband index k instead of the phase index n minus 1. So here we have this n minus 1, which is the phase, but since we don't change the phase, we can also change the notation such that instead of a phase we will have the k, the subband index at this point. And we simply drop this downsampling by a factor of n here, because we know that's what's coming out of the subbands when we deal with filter banks. Right, so in that sense we simplify the notation, which keeps the relevant information in this notation. Yeah, so compare this now with our convolution sum of equation 2 of lecture 10. Right, then it looks like the convolution sum with the phase index of n naught equals n minus 1 and with filter length equal to the block length, L equals n. So we can take a look. Here you go. So here you have this equation. Here we have our filter bank output. And here we have what we got after the index substitution. And we can see here this becomes identical to this equation if we choose n naught to be capital N minus 1. Right, then it's identical. So it's convenient. So again, we could also say this becomes then n naught minus n prime. Yeah, so we can choose n naught to be capital N minus 1, and then basically those two are the same. Yeah, and I guess I don't need those. So this indicates that yk of m contains phase n minus 1 of the downsampled subband signal. Through this comparison, we obtain the equivalent impulse response of our DFT as this. So indeed we get the time reversed transform kernel here. So we have this e to the minus j 2 pi over n, and then instead of n we have n minus 1 minus lowercase n times k. And that's the transform matrix where the rows are time reversed. So that's convenient. This is now the equivalent analysis impulse response of our DFT interpreted as analysis filter bank. So if we have our transform matrix, we can read out the impulse response of the equivalent analysis filter bank by just time reversing or flipping the rows. So observe that it can also be interpreted as a rectangular window of length n with modulation of this exponential term. So we could also see this is modulation, this exponential term, right? We already saw exponential modulation can be done with an exponential function because sine and cosine consist of those exponentials, complex exponentials. And then you would have a constant 1 in front of it, or rather a rectangular window of length capital N multiplied with this modulation function. So that also shows you how you can compute the frequency response, right? You have the rectangular window, you compute the frequency response of it, then you have the result for k equals 0, and then for the higher case you just have the frequency shifted version of it. So quite convenient. So in conclusion, the DFT can also be seen as a special kind of filter bank. Each DFT coefficient can be seen as a sample of one of the downsample subbands. Each column of our transform matrix T represents the impulse response of one of the subband filters, but in reversed order. So yeah, I was talking about rows, but I guess it's really the columns. Yeah, so here if you multiply x from the left hand side, then the impulse responses are the columns. So it depends on which side you multiply your x. If you would multiply it from the right hand side, then you would have the rows. If you multiply it from the left hand side, then the impulse responses are in the columns. Yeah. So here we have it in the columns. Each column contains the impulse response, but in reversed order. So we can read the impulse response out of the transform matrix starting from the bottom and going up. So next we come to the equivalent synthesis filter bank. So here we have the synthesis filter bank. Here we have in the beginning the upsampling to the original sampling rate, then followed by those filters that fish out the correct spectral copy. So we still need to find the equivalent synthesis filters if we apply the inverse transform, the inverse DFT, for perfect reconstruction of our signal. We get perfect reconstruction, for instance, the original signal if the transform T is invertible, which for the DFT is the case. For the mathematical formulation of the inverse transform, we can again write the reconstructed signal x hat as a sequence of blocks. So the same as for the analysis. For the analysis we have a sequence of blocks, and if we apply the inverse DFT we get again a sequence of blocks, the x hats. So x hat of lowercase m is one block of reconstructed samples. We obtain the reconstructed signal by simply multiplying the blocks of subband samples that we got from the DFT, the y of m, with the inverse transform matrix. So remember, the y of m came from multiplying the x of m with the transform matrix T, and now we multiply it with T inverse and we get back to x, or rather x hat, because we are not sure if it's the same. So the elements of this inverse DFT matrix are this. So this is the inverse matrix, position k and n, and this is the inverse transform kernel. So you can see it almost looks the same as for the forward transform, except there's a plus here in the exponent, and we have this 1 over n as a factor. And turns out this is the exact inverse of the forward transform as we applied it. So there are also other forms where the forward transform has a factor of 1 over square root of n, and then the inverse also has a 1 over square root of n, such that both have the same factor, and this is called an orthonormal transform matrix. Yeah, so this equation 5 here can also be written as, again using row times column. Here we have our yks, so the y's are a row, and here we have our inverse transform matrix. Right. So this is then the same formulated as this sum. And again with lowercase n between 0 and capital N minus 1. To see the resulting impulse response of the equivalent synthesis filter bank, we need the equations for upsampling and filtering in the synthesis filter bank. Right, so the upsampling is now the complication. In the synthesis filter bank, the subband signals yk of m are upsampled first, and we obtain the upsample signal, which we write as y upsampling capital N of index 0 and k of lowercase n at the higher sampling rate. So the 0 refers to phase 0, and we have the time index n because we are at the higher sampling rate now. The following filtering is a convolution with the synthesis subband impulse responses gk of n, and hence we get the output of the kth filter as this convolution. So first we upsample each subband by a factor of n, and then we convolve with this corresponding impulse response gk of n. Right. And here you can see it as expressed as a convolution sum. So here this convolution is just now rewritten as this convolution sum, just the usual convolution sum. So L is now the length of the synthesis filter. See also lecture 1. So in lecture 1 you can see this definition. We assume that capital L is a multiple of capital N, which we can always obtain by appending zeros if necessary. Observe that most samples of y upsampled to capital N by capital N are 0, because we insert zeros. So we can rewrite equation number 7 such that we only process the non-zero samples, and we again use the blockwise processing by substituting n by mn plus n, and the same for n prime. Right? We have then, instead of having just one index, we now get two indices. We have lowercase m for the block index, and we have lowercase n for a new in-block index. So here I use the same letter, but actually they have different meanings. So this n goes from 0 to infinity basically, or to the end of the signal, whereas this lowercase n only goes from 0 to capital N minus 1. Right, so it's a phase index. Same here for n prime. So I use the same notation because basically there's not much danger of confusion because we don't use them at the same time. Yeah, so we use those block indices m and n prime, and in block or phase indices n and n prime. And then we obtain this double sum, right? So now it makes it a little bit more complicated. Instead of having just this one sum going over the entire filter length, we now have two sums. The first goes over the in block index for each block, and then the outer sum goes over the blocks, right? But it's the same basically. We just have two indices instead of one, and we have the same range as before. So we have the same number of summons. So here now lowercase n goes from 0 to n minus 1, and of course here you can see in the sum n prime goes also from 0 to n minus 1. So here we can see that we get the non-zero elements of y upsampled of lowercase n if its argument is integer multiples of capital N, right? So this argument needs to be integer multiples of capital N, otherwise this function will be 0, right? Because of the upsampling. Yeah, and we get this if we have n equals n prime. So if n equals n prime, then those two cancel, and all what's left is mn minus m prime n. And this is an integer multiple of n. Right? We have m minus m prime times capital N, which we can then see here. Right? So what's left here of this expression is then only this. We have m minus m prime times capital N. And here we can see we can replace n prime by n because we set it to equal. And then we have a simplified expression. right? And also here, this inner sum disappears because n prime is set to n prime equals n. Right? There's only one of those summands left, so that's why this inner sum disappeared. So that made this expression now much easier. And now this expression has the advantage that it only goes over the non-zero entries of y upsampled. Right? And for the reconstructed signal, we simply add up all the n subbands. So remember, this was just for subband k, so this is partially reconstructed, just coming from subband k. And now we need to add up all those subbands, all the capital N subbands, which we do here in the next step. So the inner sum here stays the same as above, but then we go over all the subbands here, k equals 0 up to capital N minus 1, to obtain the reconstructed signal x hat for block index m and in blocks index lowercase n. Yeah, and here we can now replace y upsampled n of m capital N by the simplified notation yk of m, right? Because it's the same, since we now address only the non-zero elements. So then we get here this simplified formulation here from here to here. Now we have the yk, kth subband for block number m minus m prime. So this is now our reconstructed signal, where the first sum is over the subbands and the second sum is over the block. At this point we can compare this filter bank equation number 8 with the synthesis transform matrix equation number 6. So here I repeated this equation number 6 so that you can more easily see it. And you can see here we only have a sum going over the subbands k, but no outer sum, or no sum over m prime. Right? So this was the sum going over the number of blocks in our impulse response gk. You can see here this is the only time where we have the m prime. So the sum index n prime goes from 0 to block length, or length of the filter divided by block length n. Right. So this sum is only necessary if we have a impulse response which has block length of 2 or which has a length of 2 blocks or more. Right. So we see that we get a similar appearance if we have a length of our filter of L equals n. Right. We have no sum over the blocks, meaning the filters only have length L equals n, capital L equals capital N. Hence the inner sum disappears with m prime equals 0. So only block index 0 remains for the filter, because it only consists of one block. So with this, our equation 8 becomes this. Right? Then we just have yk of block index m times our impulse response for subband k. Right. So, and now we can actually compare the two. We can compare this with the transform equation number 6 here, and we see it's indeed identical, with gk of n equals 1 over n times this exponential function. So now we have our equivalent impulse responses. Gk of n equals 1 over n times this exponential function. And this is exactly our matrix entries. So in this case, we have the rows of the inverse matrix that are the impulse responses for our synthesis filter bank. And they are now non-reversed. Right? So for the analysis, we have the flipped columns from the transform matrix. For the synthesis, we have the non-flipped rows as impulse responses. So in conclusion, the impulse responses of our subbands are the rows of the synthesis transform matrix, here not time reversed. We can read out the impulse responses of the synthesis filter bank from left to right in each column of the transform matrix. Yeah, maybe I call this each row. Here, observe, each time we got our result by comparing the convolution sum of our equivalent filter bank with the transform sum. Right, so that was the basic approach. So here's now a Python example. Right, we take a DFT, a small DFT of size capital N equals 4, so block size 4 subbands. And then we use IPython minus PyLab for this experiment. So let me start IPython. So IPython minus PyLab in my terminal window. So here you can see it started because we have this colorful prompt. And now we can construct the FFT transform matrix by applying the FFT function to the identity matrix of size 4. So in Python, that's part of NumPy and SciPy, and in this lab we have functions FFT and not matrices. So we can obtain the matrix T by applying the function to an identity matrix, right? Then basically we have identity times internally the transform matrix, and what's left is the transform matrix. So let me do that. So I apply the function. So effectively this function internally multiplies with a transform matrix. Not really, but mathematically it does, and then the result is this transform matrix T. Right, so this is what we get. And it looks interesting because it all looks very similar except for the signs here. You can see we have different signs for the real and imaginary part, and that's how those entries differ. And that's because we just have 4 subbands. That's why we have this simple shape. Observe that we have complex values in the transform and hence obtain complex valued filters. So that's special for the DFT. So to evaluate complex valued filters, we need a full circle in the frequency domain, right? Because here positive and negative frequencies are no longer symmetric around 0. So that's why we need to go from 0 to 2 pi. If we want to obtain the frequency response of subband k equals 1 of this DFT filter bank, we take the second column, so 0 is the first, 1 is the second, time reverse it, and plot the frequency response with frag z. Right, so here you can see it. First I need to import SciPy signal as SP, because that contains frag z, which I apply here in the next row. Here I'm using my just obtained matrix T, and I take column number 1, meaning the second column here, flip it, and I apply frag z with the argument whole equals true. Whole means the whole circle from 0 to 2 pi. And then it returns the frequency sampling points W, which frag z computes, and H is the complex valued frequency response. Next I plot it with the frequency sampling points on the x-axis, and then I take the magnitude of the frequency response H, apply the log of base 10 to it, multiply it by 20 to obtain the dB numbers, and that gets to the y-axis. Here I scale the axis, here the x-axis going from 0 to 2 pi, and the y-axis going from minus 20 dB to plus 15 dB. Then the x label gets the label normalized frequency, which it is, and the y label gets the dB label, which it also is. So let me just copy. Oops. Copy and paste. Yeah, so here you go. Looks kind of funny, right? This is basically the passband of this filter. So remember, we have not the lowest one, so it's not a low pass filter, which we can also see because at frequency 0 it has a lot of attenuation. Then it has this kind of round passband. This is the passband of our subband number 1. Then here you have a transition band, and here you have the stop band. And you can see the stop band compared to the passband has, I don't know, a little bit more than 10 dB attenuation. So it's not really good. Yeah, so yeah, I forgot the title. So here you can see it with title, subband number k equals 1, and this is what you get. Yeah, and here you can also see we have this normalized frequency which goes from 0 to pi, right? So this would be Nyquist frequency, and here you have the negative frequencies from pi to 2 pi. So you can see indeed it does not have the symmetry that you would expect from real valued filters, right? The negative frequencies really here are part of the stop band. So it's stopping in the negative frequency range, and its pass band is in the positive frequency range. Yeah, so that's the peculiarity of a complex filter. Yeah, so the normalized frequency 2 pi is the sampling frequency. Since we have a 2 pi periodic frequency, this is identical to frequency 0, and the frequencies from pi to 2 pi can also be seen as the negative frequencies from minus pi to 0. So it's the same. This shows that this filter has a passband at the positive frequencies, but not at the negative frequencies. The equivalent passband at the negative frequencies is obtained from subband number k equals 3, right? So because number 4 would be Nyquist, corresponding to k equals 0, and then k equals 3 basically is counting backwards. Just like from k equals 0 we count 1 up to get the positive frequencies, so we count down from 4 to get the negative frequencies, the corresponding negative frequencies. Here k equals 3. So here we have the same code, but now we have 3 as the second index for the transform matrix, and we can plot the corresponding frequency response. Copy, paste, and I should also have the axis. Yeah. This shows you why setting the axis is useful. Copy, because otherwise we get a very funny scale. So here we don't need to go down to minus 300, and this is because the zeros here basically have a minus infinity. And to get a better scaling, we need those axes. So here you can have it now. So let me include the axis here too. Yeah. So this is what we get. So basically here you can see it's basically the flipped version now from subband filter number k equals 1. So when you compare it, here you had the positive frequency range, and when you think about flipping the entire diagram, you get this here, number 3. Yeah, so this looks like the frequency mirrored version of the filter for k equals 1. This also shows how to separate positive and negative frequencies, right? Because here now we have a filter for positive and one for negative frequencies. So the low pass is at k equals 0, and the high pass now appears at k equals 2, right? Observe that there the high pass appears in the middle because of this symmetry between positive and negative frequencies. So high pass k equals 2 would basically be around pi. Yeah, so here's an example transform as filter bank. Now we show in an example that the transform is indeed a special case of a critical sampled filter bank with the above computed filters. Right, so take the example signal of length 8. So we just take a tone, a sine of 2 pi divided by 8 times a range 8. So this gives you one period over the length of 8 samples. So then we take construct xm as a sequence of blocks. So xm of index 0 contains the first block here, first 4 samples. xm of index lowercase m equals 1 gets the second block, the second for the last 4 samples. So here's the result. You can see the first 4 samples in the first block. Here you can see the second 4 samples in the second block. And again, we obtain our DFT transform matrix as FFT of I4. So here this is the identity matrix of size 4 by 4. And then we compute the transform, the matrix multiplication with the transform matrix. Here we take xm times our matrix T, and dot is the matrix multiplication function for those two arrays. Right? So this takes each row of xm and multiplies it with T. And this is then the result. Again, we get the same shape. We get 2 blocks. Here's the first block, now containing complex values, and that's why it appears longer. Right? But it has the same number of samples. It just turned the time domain samples into DFT coefficients. So each row contains the spectrum of each corresponding block. So here's the spectrum of the first block. Here's the spectrum of the second block. And again, you can see here small numbers, 10 to the minus 16. And when you see something with 10 to the minus 16, then you know it's a rounding error and it should really be 0. So this should really be 0 in this case. Everywhere you can see e to the 10 to the minus 16, e minus 16, it means basically 0. Like here. So here it had precise 0, here you have rounding errors. So now we process the input signal x through a critical sampled filter bank with the equivalent impulse responses, the transform matrix columns, flipped up down and downsampled with the last phase of the blocks n naught equals n minus 1 equals 3, as it appeared in our derivation of the equivalent impulse responses. So now basically we want to get the same result that we obtained from our transform, but using a filter implementation, which you can see here. So here we're using L filter, which implements the filter convolution. You can see flip up down T for the kth column. So this is our filter impulse response. And then you can see here this 1 refers to the feedback path, which we are not using here, that's why it's a 1. And then x is our signal, our sinusoid. And we just take the samples from 3 to 4 because we do we start at sample number 3, right here, n naught is sample number 3, and we downsample by a factor of n, capital N equals 4, right? So this is now the downsampling. So you can see this is actually a less efficient implementation, because first we do the filtering, we obtain all the samples, and then we just keep every 4th sample starting with sample number 3. So this is much more wasteful than the previous implementation, but it should result in the same output. Right. So here you can see it does the filtering for all the filters, for k in the range of 4. So it goes from k equals 0 to k equals 3. Yeah, and in the end you should have our subbands. So here you get the subbands for each column, you get the filter output, and that's done for each k. So here again you can see the output, and now you should be able to see that it's the same. So here each row contains the coefficients from the DFT. That means the first entry of the first row contains subband number 0, first sample. And then the next row we have subband number 0, next sample. So here we have 2.4. And again here for the filter bank implementation, again we have 2.4. And here next minus 2.4. It's the same here. Right, so here each column is each subband. You can see it here. K denotes the column. So here k equals 0 gets us the first output, the first subband. Then here the next entry is subband number 1. We have -1, +1, and the rest is 0. Same here, -1, 1, and the rest is practically 0. So we have identical outputs, and that shows that it works, right? If we would have different outputs, then we know there's a problem, but this confirms what we just derived theoretically. So it's doing the same thing. So we can see that yt from the transform and y from the critical sampled filter banks are indeed the same. So in conclusion, we see that a transform is a special case of a filter bank. The tool of reading out the impulse response from a transform matrix allows us to analyze the resulting filters and to judge if they fulfill our requirements or not. So here in the case of a DFT, we saw that the filter is actually not really good. So it probably doesn't fulfill our requirement. Okay, so that's it for this set of slides. Thank you for your attention and see you next time.